Ever stop and wonder what's really going on when you see a planet in orbit? Or how about something more down to earth, like what really determines the outcome of a car crash? Well, today we're pulling back the curtain on the invisible rules, the physics that govern literally everything that moves. So here's how we're going to break it down. We'll start by questioning the very idea of what it means to be moving. Then we'll learn the language to actually describe it properly. After that, we'll uncover its hidden oomph, and finally, we'll get to the universal laws that run the entire show. All right, first things first, let's tackle a question that sounds simple but is actually surprisingly tricky. What does it even mean for something to be moving? I mean, the answer seems obvious, right? The bus is moving, you're not. But what happens if we completely flip our point of view? And here's the kicker. Both of these are completely 100% correct. It turns out motion depends entirely on your frame of reference, on what you consider to be standing still. To a passenger on that bus, the world outside, including you, is what's zipping by. And that gets us to a really core idea in physics. To even talk about motion, you need what's called a reference frame. Basically, a background that you just assume is fixed. We almost always use the Earth as our default reference frame without even thinking about it. But as we just saw, that's a choice, not some kind of universal rule. Okay, so if motion is relative, how in the world do we talk about it precisely? Well, that brings us to our next section, the actual language of motion. We've got to get beyond just saying things are fast or slow. So the most basic measure we've got is speed. You know this one, kilometers per hour, meters per second. It's super simple. It's just how much ground an object covers in a specific amount of time. And the relationship between speed, distance, and time is incredibly straightforward. You can even use a little trick with the table like this. Just cover up the thing you're trying to find with your finger, and the other two show you the formula. So cover distance, and what's left? Speed times time. Pretty cool, right? But speed alone doesn't really give you the full story. If someone tells you a storm is moving at 50 kilometers an hour, that's not super helpful. Is it coming at you or moving away? For that, you need velocity. Velocity is speed with a direction. So 50 kilometers per hour east, now that's velocity. Now, this is so important. We usually think of acceleration as just speeding up. But in physics, it's any change in velocity. That means slowing down is a type of acceleration. And, get this, even a car driving at a perfectly constant speed around a curve is accelerating because its direction is constantly changing. So now that we have the right words to talk about motion, let's explore that hidden oomph behind it. You know the answer to this intuitively, right? It's just bigger. That quality you can almost feel in your gut just thinking about those two vehicles, that's what we call momentum. Momentum is essentially the quantity of motion an object has. That truck has a huge amount of mass, so even if it's going the same speed as the car, its momentum, its oomph, is absolutely enormous. And that's what makes it so much harder to stop. And this idea leads us to one of the most powerful and fundamental laws in the entire universe, the conservation of momentum. It means that in any interaction, whether it's two cars colliding or a star exploding, the total momentum before is always the same as the total momentum after. It doesn't disappear, it just gets transferred. On a very practical level, this is exactly how investigators can piece together what happened in an accident. So what causes momentum to change in the first place? What actually creates that acceleration we talked about? Well, it's time to meet the invisible players in all of this, forces. It's really that simple. If you see an object accelerate, and remember that means speeding up, slowing down, or changing direction, you know for a fact that an unbalanced force is at work. No acceleration can happen without a force. Period. Now, forces love to work in teams. When they're balanced, like in a perfectly still game of tug of war, they just cancel each other out. Nothing happens. But the second one side pulls just a little bit harder, the forces become unbalanced, and that rope starts to accelerate. And in our everyday lives, two forces are pretty much running the show. You've got friction, that's the silent hero that stops a rolling ball and literally lets you walk without slipping. And then you have gravity, that relentless pull that keeps us on the ground and guarantees that what goes up must come down. Okay, time to put it all together. Let's look at the three simple yet incredibly profound laws that Isaac Newton figured out. Laws that describe pretty much all the motion in our universe. These three laws, they are the absolute bedrock of classical mechanics. They elegantly explain why things stay put, why they move, and how they interact with each other. From the orbit of a planet down to a couple of billiard balls colliding on a table, everything is playing by these same three rules. And here's the really crucial part. These are not just some abstract rules in a textbook. They describe physical experiences you have every single day. Think of them as the invisible operating system that's constantly running our physical world. This brings us to a final thought, a classic physics puzzle. If every push has an equal and opposite pushback, how does anything move at all? If you push on a wall and it pushes back with the same force, shouldn't those forces just cancel out? Well, the answer is the key to everything we've talked about. The forces are acting on different objects. Your push is on the wall. The wall's push is on you. To actually move the wall, your push just has to be greater than the other forces holding the wall in place, like friction. It's a beautiful little puzzle that just reminds us that even in the simplest actions, there's a whole universe of physics at play.